Hello everyone. In the previous two lectures, we had been talking about uh, one paradigm of 2D elasticity, uh, which was plane stress, and we went on to discuss the eddy stress function approach and ended up at the end of those discussions with this biharmonic equation, which included within it uh, almost all the information conveyed by the compatibility equation, the constitutive law, and the stress equilibrium equations. Now let us see if we can do the same sort of thing with the other paradigm of the 2D elasticity, which is the plane strain. So we start with plane strain today. So just like in plane stress, we started out with a canonical physical example. So also here we'll take uh, uh, we'll start with a similar approach. So we considered uh, an infinitely long body which has a uniform cross section. So something like this. So when I say infinitely long, I basically mean to say that uh, it is extremely long compared to its other dimensions. So let the cross section be of this fashion. Let's see if we can join this up. Going to be a little bit problematic. Let's see if we can do this better. So we have this sort of a situation. Okay, that's better. Now, uh, what we say is that the loading on this is taking place in a special fashion. So what we basically mean is that suppose we consider that this is uh, our z-axis, this is our x-axis, and this is our y-axis. Then the loading that is taking place on the lateral surface of this body, lateral means this one, okay, this surface, not this surface or this surface. So uh, the loading that is taking place, uh, it is not varying along the z direction, so it is uniform along this direction. Furthermore, it has no component along the z direction. So if I have to represent it, the loading will be, as a specific example, it can be like this. I'm copy pasting the first arrow just to give you the idea that it is perfectly uniform. Okay, what cannot happen is that we cannot have a loading which is like this, okay, which has a component along the z direction. That cannot happen. Okay, so that is wrong. So we remove that. Now when we have this kind of a situation, and you understand that this loading is going to continue all along the length, okay, so it is not just within this zone that this loading is taking place. So when we have this kind of a situation, and please note that even though I have drawn it as an example in the form of tractions, okay, applied loads here, it can very well be also in the form of a body force, and that body force also has to satisfy this property that it cannot have any component along the z direction, and the body force must be uniform along the z direction. So when these conditions are satisfied, then what is going to happen is that the deformation field can be taken to be only a function of x and y. Furthermore, the displacement along the z component, that can be taken to be 0. So what we say is that uh, so if body forces and tractions are uniform along z, and do not have any z component, then u, the displacement along the x direction, that will be a pure function of x and y. So v, the displacement along the y direction, that will be a pure function of x and y, and w is going to be 0. Okay, so we are not going to have any displacement along this z direction. What this basically means is that we are allowed to consider any generic slice. Okay, we are allowed to take any generic slice uh, like this within the body, and it is guaranteed that no matter where we take the slice along the z, the displacement field is going to be the same in all of those slices. Okay, so it is somewhat reminiscent of that thin plate like situation. So if you think of this slice or the cross section of this slice like the mid plane of the plane stress condition, it is somewhat reminiscent of that, but there are important differences as far as the strain fields and the stresses are concerned. So talking about the strain fields, we can immediately launch into a discussion of that by noting first of all that epsilon xx using the strain displacement relations, so this is going to be a pure function of x and y. The epsilon yy similarly is going to be a pure function of x and y, because u here is a pure function of x and y and v is a pure function of x and y. Similarly, epsilon xy, which is given by del u del y, half of del u del y plus del v del x, that is also going to be pure function of x and y. Now epsilon zz, however, that is given by del w del z, and since w is 0, the epsilon zz is 0. Furthermore, epsilon zx, that is equal to half of del w del x plus del u del z. Now w is identically 0 and u is a pure function of x and y, so this term is 0, so this is 0. Epsilon yz is equal to half of del w del y plus del v del z, and here also w is 0 and the del v del z is 0 because v is a pure function of x and y. Okay, so what transpires is this, that unlike the plane stress condition where the epsilon zz was not equal to 0, okay, so here it turns out that epsilon zz is 0, the epsilon zx is 0, and the epsilon yz is 0. So there is a clear-cut distinction with the plane stress condition. Okay, so here this is 0. That's very important. So please note this. All right. Now, what we want to do is proceed in a similar fashion to uh, the plane stress things. Okay, so first of all, what we note is what happens or what simplifications to these kinds of relations. Okay, the fact that epsilon zz is zero uh, among these among other relations like this. So what simplification does it afford when we talk about the constitutive law, basically the generalized Hooke's law? So let's consider that in the next page. So first of all, we have the epsilon xx, that is equal to 1 by e sigma xx minus nu sigma yy plus sigma zz. Now please note that when we were talking about the plane stress condition, we could immediately set the sigma zz to be equal to 0. But here we are talking about the plane strain condition. In the previous page, we had not talked about anything to do with the stress components. So right now, a priori, I don't have any information to say about the sigma zz. So let us keep it like it is. Similarly, for epsilon yy, I have 1 by e sigma yy minus nu sigma xx plus sigma zz. Again, I can't say anything more about this. Epsilon zz, however, is 0, so perhaps there is some hope here. If we set epsilon zz to be equal to 0, as seen on the first page, on the previous page, then what we obtain from here is that sigma zz is equal to nu times sigma xx plus sigma yy. Now this is new. Okay, this is something new, something fresh, and we can actually utilize this relation back in these two equations. So let's do that. Okay, so let's use this here to see what we get. Okay, so epsilon xx is equal to 1 by e. So when you substitute the sigma zz with this, uh, what we have here is sigma xx uh, minus nu sigma yy plus nu sigma xx plus nu sigma yy. So that is going to give me 1 by e 1 minus nu square sigma xx minus nu times 1 plus nu sigma yy, and from that I can actually take out the 1 plus nu out to obtain this. Again, when I use this relation back here in the epsilon yy, what I will obtain is just like I had obtained the expression for epsilon xx in terms of sigma xx and sigma yy, I will obtain this relation. Okay, 1 minus nu sigma yy minus nu sigma xx. All right, for the other terms, let's see what happens. Epsilon xy is equal to 1 plus nu by e. So basically this is 1 by twice g, that is sigma xy. So you understand that because in the plane strain condition, the epsilon xy in general is not 0, so sigma xy is not going to be 0. Epsilon yz, however, is 0. Okay, so epsilon yz is 0, which implies that sigma yz is 0. So that is just like the plane stress condition. and finally epsilon zx is also 0, and so the sigma zx is also going to turn out to be equal to 0. Alright, so sigma yz was 0 in plane stress, sigma yz is again 0 in plane strain. Sigma zx was 0 in plane stress, sigma zx is again 0 in plane strain. However, in plane stress we had sigma zz to be equal to 0, but in plane strain sigma zz is not 0. Okay, so we have some important differences between the plane stress and the plane strain conditions already just by the first consideration of the constitutive behavior. Now, if we look back at the plane stress formulations, okay, the mathematical framework that we developed using the under the plane strain, the plane stress paradigm, what we did was to next consider the compatibility equations. Okay, we motivated the entire discussion surrounding the Airy stress function by considering the stress equilibrium equations, definitely, but it was only much later, after we had considered the compatibility equations, that we actually incorporate the information from the stress equilibrium equations, and that is exactly the route that we'll follow now. So after we have considered the compatibility equations, we are going to consider after we have considered the constitutive equations on this page, we are going to consider the compatibility equations. But you just note for a second that what is happening to the stress equilibrium equations. We are not going to do anything with it, but you just note what is happening. So del sigma xx, okay, so this is just like a side note, okay, just to be aware of what we have managed to do till now. Let's take a look at the stress equilibrium equations, but we are not going to utilize this right now. So very quickly we'll look at it. And again, we don't consider the body force right away, exactly in the fashion that we had proceeded in the plane stress case. So you see the sigma zx is very much 0, okay, 0 here, so that goes away. So the first equation is very much like the first equation that we had in the plane stress case. From the second one, we have del sigma xy del x plus del sigma yy del y plus del sigma yz del z. And again, you note that this term is 0, which means that the second equation of the plane strain stress equilibrium equations, that is also looking exactly like the plane stress case. But what about the third one? So here we have del sigma zx del x plus del sigma yz del y plus del sigma zz del z. All right, now you see here in this relation epsilon xx has been expressed in terms of sigma xx and sigma yy. Epsilon yy here has been expressed in terms of sigma yy and sigma xx. Fine. Now if we were to revert these equations, then we would be able to obtain expressions of sigma xx and sigma yy separately in terms of epsilon xx and epsilon yy. So that is just a matter of algebra. We don't actually have to do it. We just need to note that it is possible to find out expressions of sigma xx and sigma yy separately in terms of epsilon xx and epsilon yy. Now the important point that I want to drive home here is that individually epsilon xx and epsilon yy are pure functions of x and y, which means here that sigma xx and sigma yy are also functions of x and y, which means in turn that if we come to this relation, sigma xx is a pure function of x and y, sigma yy is a pure function of x and y, which means definitely that sigma zz must be a function of x and y, which means that this term here is going to be 0. So this is 0, this is 0, this is 0. So overall you see that we have ended up with only these two equations involving the sigma xx, the sigma xy and the sigma yy, just like as we had done in the case of the plane stress case. Okay, and this is very, very interesting, and it gives us hope that whatever we were able to do with the Airy stress function approach in the plane stress case, we should be able to do it in the plane strain case also. Of course, there are going to be some differences, as we'll see. So proceeding exactly like the plane stress case, what we'll do is first consider the compatibility equations. So when we consider the compatibility equations, it will turn out, okay, so it will turn out that it is only the first of the strain compatibility equations. So this one, del square epsilon xx del y square plus del square epsilon yy del x square is equal to twice of del square epsilon xy del x del y. That is the only equation which is not going to turn out to be a 0 equal to 0 form, because if we just quickly look back at that previous page where we considered the compatibility equations, you see everywhere. So for example, so let us consider the other equations just very quickly. Okay, so uh, all the terms which we deleted based on the dependence or based on the derivatives with respect to z, that is still very much true, because here in the plane strain case also we have the epsilon xx and epsilon yy to be pure functions of x and y. So this term is again going to cancel out. The epsilon zz now is 0. So this second equation which gave us this thing, that is again going to turn out to be a 0 equal to 0 form, because epsilon zz is 0. This one also is going to give us a 0 equal to 0 form, because in the plane strain condition epsilon zz is equal to 0. Note here that in the plane stress case, this one turned out to be 0, primarily because of the fact that we had yz, epsilon yz to be 0 itself, epsilon zx to be 0 itself, which we also have in the plane strain case, and epsilon xy was a pure function of x and y, which is very much true here, and similarly the epsilon xx is a pure function of x and y. Similarly for this equation also, so in the plane strain case also this is going to turn out to be 0 equal to 0. And finally you see this last equation where we had this term remaining because of the non-zero epsilon zz, but now we do have the epsilon zz to be equal to 0 in the plane strain case. So this is also going to be equal, turn out to be 0 equal to 0 form. So these 5 equations, they are all going to be 0 equal to 0 form. Only the first of the strain compatibility equations is not going to be the 0 equal to 0 form. Something substantial is still remaining there, just like the plane stress case. And this is very good news actually, because when we proceeded from here, we neglected this equation, and this equation, and that was an approximation. If you just if you rewind the video for that lecture, you will see that that was, I did mention that as an approximation, but as it is turning out that all these equations are 0 equal to 0 form, and this is the only meaningful equation remaining. So this is no longer an approximation in the case of the plane strain paradigm. Okay, so let's get back to where we were. Okay, so this is the only substantial equation that we have from the compatibility equations, and what we are going to do here is substitute the expressions of epsilon xx, epsilon yy, and epsilon xy using these relations. Okay, and we are going to do that in the next lecture. So we have already covered substantial ground in this part of the lecture. So in the next lecture we are going to substitute these expressions in terms of the sigma xx, sigma yy, and the sigma xy. So I'll end this part of the lecture here. Thank you very much.